Hello and welcome to the NPTEL online certification course on microelectronics devices circuits. Today we will start with a new chapter or a new section as per the syllabus, and the chapter is on operational amplifiers and its terminals. The name of the module is ideal operational amplifiers and its terminals. What we will be doing in this module is the following. We will look into what is known as an ideal op amp. When we say op amp, we mean to say operational amplifiers, and we will see why is it named so. We will look into the function and characteristics of an ideal operational amplifier. Then we will be looking into the differential and common mode signal here, right, and then we will come to non-inverting, inverting mode, and then we will finally recapitulate our discussion. And now way back in 1960s or around 50s and 60s, you had the first operational amplifier being designed, which was in IC form, and so it was approximately in 1960s or 65s. You had this operational amplifier, which was named as mu A 709. So this was the first sort of an operational amplifier which was designed. It consists of large number of resistors, it consists large silicon area, right, and the silicon area was typically very large in this case. As a result, it also consumed very high power. So the power was also very high, right, and this was in the analog block available to me. So it was basically an analog block, and as I discussed with you, this analog block did consume large amount of power, but this was the first time we are able to have a look into the operational amplifier. What does the operational amplifier basically means? It primarily means that it senses the difference between two voltages and then amplifies it to have a output voltage which is just a difference of the two voltages. So if I have got two voltages, maybe sine wave, two sine waves, and then we subtract the two and then multiply with the fixed gain value A, and that is what the output is all about. So that is the reason it is also referred to as a difference amplifier, right. It is also referred to as a difference amplifier. Why difference? Because it is actually trying to look into the difference of two voltage sources and trying to find out the output voltage depending on the difference of the two voltage sources. Now the idea was, and why it became famous, or operational amplifier was used quite often in large amount of instrumentation design, was first of all its versatility, right, versatility. So the first reason why it became very famous was versatility, and the reason why it is so versatile is that you put this operational amplifier anywhere within the structure, wherever you have an analog signal, or for that matter even a digital signal is available to you, but primarily 90% of the cases analog signals. You can do large amount of computation in analog domain using operational amplifier, right. So you can add two signals, you can subtract two signals, you can do multiplication of two signals, you can do cascading of two signals, so on and so forth. So this was not possible earlier, remember. It was possible through a bipolar technology, but operational amplifier through bipolar technology is also available to us, and the gains are relatively very high. So you get a large gain and you also get versatility, and you can use this across many signal domains. The second thing is its robustness. It is quite robust in the sense that the offsets or the variabilities are very low in this case. So if you have designed a op amp which is say working with an amplification of 100, then you will be 100% sure, or you will be pretty sure that the gain is fixed at 100, irrespective of the ambient, irrespective of the variations in the parameters of the devices used in the operational amplifier. It is almost fixed at approximately 100, right. So it is two advantages, it is versatility and it is very robust in design. That was the reason op amp is still a very important IC whenever you are using it in, especially in analog and mixed signal blocks of your VLSI design. Let me show you how an ideal operational amplifier looks like. Ideally for a user, the ideal operational amplifiers look like this, which is this one, and it has got three terminals here. Terminal number 1, so this is terminal number 1, right, this is terminal number 2 here, and this is your terminal number 3, right. So, there are 3 terminals and there is a specific sign to the first terminal minus, specific sign to the second terminal plus, and you have an output here which is V out. So, this is your output terminal. So, terminal number 1 and terminal number 2 are basically your input terminals, right, and terminal number 3 is your output terminal. So, it is basically a 3 terminal structure wherein the first 2 terminals 1 and 2 are basically your input terminals and the structure 3 is output terminal here. Now, since this is an active device, obviously these operational amplifiers are actually made up of differential amplifiers that you possibly be knowing also, or maybe I can give you an extra talk on that, but these are internally they are made up of differential amplifiers, which we have already studied on our earlier modules. So, you require an external power source to drive these operational amplifiers, and this is where this 4th and 5th terminal come into picture. We generally do not show these terminals, or we do not show whenever we are drawing an operational amplifier, we do not show it, but typically these remain there, and this is given as plus VCC here and a minus VEE here. So, I have a plus VCC here and I have a minus VEE at this particular point. Obviously, this is the 3rd terminal which is available to you. Now, therefore, I can therefore correlate this to this terminal, that terminal 4 is biased in this manner such that the positive terminal of VCC is connected here and the negative terminal of VE is connected to terminal number 5. So, I have got therefore typically at this stage understanding purposes 1, 2, 3, 4 and 5. 4 and 5 are primarily DC biases, 1, 2 are input and 3 is the output. Now, if you look very carefully across this network here which you see here, these are the DC biases which you apply, and here you apply the AC signal, right. So, so sort of a mixed signal approach is here, but these DC biases is done in order to saturate or in order to make those transistors or a bipolar transistor or even a MOSFET in the active region of operation, so that they start behaving like a current source and you do have a large gain available with you. So, this is the basic structure of an operational amplifier, and basic structure looks like this in a real sense. So, let me show to you, or let me give you an idea about what the idea is. The idea is something like this. So, if I have got as I discussed with you that I have a operational amplifier like this, right, and I have got negative and positive. So, this is your this is your this. This terminal, negative terminal, is referred to as an inverting terminal, and this is referred to as a non-inverting terminal. Inverting terminal primarily means that any signal you give here, right, will be inverted or will have a 180-degree phase shift between input and output, where terminal number 3. So, this is your output V out, and this is always measured with respect to ground. So, all of these measurements, so this is your V out. So, all these measurements which you do here, this is with respect to, so this is V in 1, let us suppose, again with respect to ground, and then you have got V in 2 here again with respect to ground. So, all are with respect to ground here, and whatever signal you give on a non-inverting terminal here will appear as 180-degree phase shift. So, if you have got something like this, it will appear something like this in the output side, whereas in the non-inverting terminal, if you give like this, output will be something like this, right, and you have to ensure that. So, they will be in phase. So, if I talk of non-inverting terminal, inverting, then I will have V out and V in are in phase, right, in phase, and if you have got inverting terminal, then V out and V in will be 180-degree out phase. This is quite important, and therefore let us suppose this is V1 and this is V2, then my output looks like the V out, or say V out in this case will look like A multiplied by V2 minus V1. This will be the general equation of ideal operational amplifier. Now you see it is V2 minus V1, why? Because it is connected to the inverting terminal. So whatever input you give, it will be always phase shifted by 180 degree, whereas V2 is basically my inverting terminal. Now when I so whatever signal I am giving is the difference between the two signals is basically my output multiplied by A. A is referred to as a open loop gain of operational amplifier. So A is defined as the open loop gain of the operational amplifier, which means that A basically this is the gain of the differential amplifier which is there within the operational amplifier, right, and therefore you get V out to be equals to A times V2 minus V1, right, and this is what general scheme of things appear here. Now what you see in this case is that if you look, now let us draw its appropriate circuit diagram, its equivalent circuit diagram. So if you see here, I have an inverting terminal, I have a non-inverting terminal. It has been seen that the input of my op amp is having Zin, which is input impedance, to be ideally infinite, which means that the current is actually equals to 0. So no current is entering into the terminal of op amp, right, and you can understand from your basic theory also. See, if you remember from your differential amplifier, the two inputs are towards the gate, remember the gate of the MOSFET, right. Now the gate of the MOSFET automatically, if you remember, has got a very high input impedance because there is an oxide layer and therefore it is dielectric, and that is the reason you do not have any current flowing through the gate side, right, almost 0 current, which means that the input impedance is relatively very high. In ideal op amp, the input impedance should be infinitely high, which means that your voltage remains fixed, right, and your current is almost 0, whereas in the output side your Z out will be equals to 0 in an ideal case, which means that you can draw any current you want to do, right, you can draw any current and typically your voltage will remain fixed, or otherwise the current will remain fixed and you can vary any voltage which you want, del VOT. So how I define my Z out? Z out is defined as del V out by del V in, right, del V in, which means that del V out should be equals to 0, which means that I should not see a change in the voltage with change in current. So I can do a large variation in the current in the output domain, but my voltage across the terminal 3 and ground should remain fixed, and therefore that is my 0 output impedance which you see here. I will come to this point just now, but let us concentrate here that open loop gain again for an ideal operational amplifier is infinitely high. So and its infinite bandwidth, both of these statements are for ideal operational amplifier, which means that if you are able to plot if you plot voltage, if you plot gain versus omega or frequency for operational amplifier, right, it will look something like this for ideal case. It will be infinitely bandwidth and the gain is always fixed and the gain is always fixed and very high gain, infinite gain. So this will be around infinity, right, and that is what is happening here. Now you see here within the blue triangle, which is a schematic of the op amp, this is the voltage which you see, A times V2 minus V1. So it is a voltage source here, and therefore the output is given as A V2 minus V1 for all practical purposes. We come to this one now. See, it tells me that common mode gain is 0, which means that if any signal which is common to terminal 1 and 2 will always be rejected. So if I have V1 equals to V2 equals to 1 volt, then of course ideally my V3 or V out will be equals to A times V2 minus V1, and therefore A times 1 minus 1 will give you 0. So my V out will be equals to 0, which means that any signal which is common to both the terminals will be automatically rejected or will not be accepted, or gain will be almost equals to 0. This is known as a common mode gain. Your why? Because you are giving a common signal to both the inputs of your operational amplifier and therefore their gain, right, and therefore your so common mode gain is high. Now but my differential gain is relatively high. Why differential gain? Because differential gain by definition, if you see, is V out is equals to A times V2 minus V1. This is your differential gain. The difference between the two signal gets amplified by a large value which is infinitely large in ideal case, and therefore this will be infinity large, but we will see that it does not work. It will never be infinity, it will have some values associated with it. And can you tell me why it will not be infinity? Can you think about it, why will it not be infinity? Even if your A is infinity, the reason is, see, I discussed with you just now that in the previous slide that this is limited by plus VCC and minus VCC. So, if a plus VCC is plus 15 and let us suppose this is minus 15 volts, right, you do anything you want to do, the V out value cannot exceed plus 15 in the positive cycle and cannot exceed minus 15 in the negative cycle, because these are limited by the power supply here. And if it crosses, there will be clipping, and therefore what you can see is that if the if typically the A value is large, I will expect to see something like this, clips. So, it will clipping at plus 15 here and it will clip at minus 15 here, and so your distortion will take place, right. And therefore, an ideal op amp has got a 0 common mode gain and has got a large infinite gain with you, right. So, let me come to the next case and let explain to you the differential and common mode signal. So, I would say differential signal VID will be given as the difference of the two signal V2 minus V1, whereas common mode signal is given as the average of the two signal V1 plus V2 by 2, right. So, what is common mode signal? Is a common mode signal, as you can see here, is basically a DC bias which is given to or even an AC bias which is given to common to both the terminals, inverting and non-inverting terminal of my design. You will ask me why is it given? Well, this is given very simply because that you want to bias it in the active region, both the MOS devices, remember. So, you need to give an external bias which will try to do it. That plus we will see later on that it has to do with noise of the source also. So, I get VICM equals to V1 plus V2 by 2. Therefore, if you just place it and do some manipulation here, I get this V1 equals to VICM minus VI by 2, and I get V2 to be equals to VICM plus VID by 2. So, I have a VICM and then the voltage goes up by VID by 2 and it comes down by VID by 2 and so on and so forth, right. So, this is the output voltage which you see, or the input voltage with this what you see, right. So, let me recapitulate what we learned and then we will go for negative and inverting terminal, non-inverting terminal in a general sense. So, ideal op amps will have infinite bandwidth, large gains, A will be also infinitely large. These are basically input impedances are relatively very high, Zn equals to infinity, and output impedance is 0 in reality. These are again direct coupled or DC amplifiers. We will discuss this later on as time permits, but these are known as direct coupled or DC amplifiers, right, because they are able to amplify signals which are very low frequency signals. So, even at a very low frequency, a good amplification is available when you do an operational amplifier design, right. With this knowledge, let me come to a very important configurations now, which means that op amp by itself has got no use until and unless you do have a supporting configuration to help it. For example, this is the first configuration which we will be studying and known as inverting configuration. As a result, what we will see later on is that this configuration helps you to invert a signal, analog signal. So, if I have a sine wave, I will actually get automatically, I will get a sine wave, 180 degree sine wave, and I can change the gain of the output waveform also. So, how it is done? It is done in this manner. This positive is grounded, my non-inverting terminal is grounded here, and the inverting terminal is connected across R1 and R2, and through this thing they connected to the V out value here. Now, the current flowing through this R I1 will be equals to V1 minus V2 VI minus V1, which is the voltage, this is V1. So, Vi minus V1 by R1 will be the voltage which is the current flowing through this arm I1, right. And similarly, I1 can be written as Vi by R1. Why? Because you see, and this is quite interesting, that this is concept of virtual ground, that in an operational amplifier, since my Zin equals to infinity, right, voltage at arm number 2, arm number 1 sorry, here will try to actually equalize itself to arm number 2, because remember Zin was defined as Vin by Iin, right. Now, I told you that input impedance is infinitely high, so Iin will be equals to 0. 0 means this will go to infinity and Zin equals to 0. Similarly, I can also define it in this manner that my V, so that is the reason you get infinity large bandwidth, but this point number 1 is also referred to as a virtual ground. Why is it referred to as a virtual ground is that if you remember, a ground is a place where you will have high currents and low voltages, because low voltage because you are grounding it to the ground, high current because since it is grounded it is a 0 potential, all the current will flow through it. Here interestingly one will follow 2, so its voltage will be around ground, so it will be very very low voltage, but there will be no current flowing through into this because it is a high impedance node. So therefore they are referred to as a virtual ground, right. So though they are grounded, though their voltage is 0, but you do not get any current into it or out of it, and therefore they are known as input, they are referred to as this thing. Similarly, so therefore if I have infinitely a large value, I get V2 minus V1 equals to V0 by a, right, because V0 was equals to a into V2 minus V1, I took it denominator, a is infinitely large, so I get V2 equals to V1, which means that V1 equals to V2. That is what I was talking about, that whatever voltage is there at terminal 2, terminal 1 also starts to go towards that voltage, right. This is because of an infinitely large value of amplification open loop gain of my operational amplifier. With this knowledge I do a small derivation and I get V0 by Vi equals to minus R2 by R1, right, minus R2 by R1. Now this is known as an inverting configuration, inverting configuration. Why inverting? Because you have a negative sign here, which means that the input and output will be 180 degree out of phase, right, and it's this, now this is referred to as a closed loop gain. Closed loop, why? Because now your loop is been closed by R2 and R1. Open loop, when you open it up we define different open loop gain, that will be just the amplifier gain which you see here, which means that the closed loop gain will be relatively much smaller as compared to an open loop gain. Typically A is of the order of 10 to the power 4, 10 to the power 5 maybe, or even 10 to the power 3000 volt by volt, whereas this might be very very low, maybe 100 or maybe 10, 20, whatever. So what we have done is that using this negative feedback concept we have actually reduced the gain, right, but my gain is more stable now, and it does not depend upon the open loop gain of the operational amplifier which I am using here. That is the major advantage. So therefore by simply changing the value of R2 and R1 you will have various values of the output voltages in the case of inverting configuration. In the inverting configuration, let me show you the corresponding corresponding circuit diagram. This is an equivalent circuit diagram which is there with us, and therefore I can show it to you that in this case for example I can write down that say this is your R1 R2, and therefore this is the voltage difference V2 minus V1 because they are inverting and non-inverting terminal. You multiply A into V2 minus V1 and you get 3 here. Now therefore as I discussed with you, V1 is approximately equals to 0 because it is a virtual ground, and therefore the current flowing here is Vi by R1, and the same current will flow through R2 because there is no other path for the current to flow down, and therefore at this output terminal I get output will be equals to 0 minus, why 0? Because this is grounded, and therefore 0 minus the voltage drop here will be nothing but minus times Vi by R1 into R2 because this is the current multiplied by this resistance will give you the voltage drop here, and that must be equals to V out. So V out I get equals to minus R2 by R1 into, so V out equals to minus R2 by R1 into V1. So if I take Vi down here as a denominator I get minus R2 by R1 as my explanation. So that is the reason why we get virtual ground in a detailed manner, right, and we get a typical virtual ground here. Now the second aspect is that let me see effect of a finite open loop gain, which means that till now when we are dealing with your operational amplifier per se, we were looking into the fact that we were assuming that the gain is infinitely large. In reality not true. Whenever you have a closed loop gain, for example a feedback loop here, R2 is feeding back into the input side, you do have a finite open loop gain. So your open loop gain is not infinitely large, right, and you get a finite open loop gain. So let me see, let me explain to you how do I get finite open loop gain. So I get current I1 equals to Vi, right, minus V0 by A. Why V0 by A? By R1. V0 by A is output voltage by A will give you the difference in the input voltage. So Vi minus that by R1 is the current. So I get Vi plus Vo by A by R1 equals to I1. Now this I1 flows through R2, R1 and R2 the same current is flowing. So I get V0 equals to minus V0 by A minus I1 into R2, right, and therefore, I get minus V 0 by A minus of V I plus V 0 by A divided by R 1 into R 2. Just I have replaced I 1 by this one. If you do a small, so gain which is the closed loop gain, I get V 0 by V I equals minus R 2 by R 1 divided by 1 plus R 2 by R 1, right, R 2 by R 1 divided by A. This gives you the value of G. Now, as A tends to infinity or very large value, this quantity goes to 0 and G tends to minus R 2 by R 1. So, you see from this formula or from this definition, I can achieve a infinite open loop gain. If A is infinitely large, I get my closed loop, this is my closed loop gain, G is my closed loop gain will be equal to minus R 2 by R 1, right. So, the condition, therefore, the condition is 1 plus R 2 by R 1, this should be as small as compared to A. When this is as so A is, if it is very large, you automatically get this into consideration, right. So, this is the effect of finite loop gain. So, I get R I equals to R 1, right. Let me come to the, if you have understood inverting and non-inverting is just the complementary of that. So, non-inverting configuration will come. In non-inverting, what we do, we apply the signal to the non-inverting mode, but we have the same configuration of the closed loop gain and R 1 and R 2 here. So, if you solve it, I am not doing it in the class, I am not doing in the module, if you solve it, I get V 0 by V I equals to 1 plus R 2 by R 1. So, what are you getting in the inverting mode was minus R 2 by R 1, here you are getting 1 plus R 2 by R 1 and with the positive sign. With the positive sign primarily means that they are in phase. So, this V I and this V O, this V I and this V O will be in phase in all respects, right. You can do a small derivation to get these values of V O and V I, they are very simple, straightforward. I would expect you to do it if you know what is the Kirchhoff's law and how you know you solve a Kirchhoff's law. So, I get 1 plus R 2 by R 1 as the gain for this case, right, and that is what the gain which you get in this case, right, and that is what we get for all practical purposes. Again, if you take a finite open loop gain in case of a non-inverting terminal, I get this into consideration, that I get gain equals to V 0 by V I 1 plus R 2 by R 1 upon 1 plus R 2 by R 1 by A 1 plus of this one. So, now in this case also, if A is very large, V is very large as compared to 1 plus R 2 by R 1, then what you get is that this automatically vanishes and I get open loop gain, closed loop gain to be equals to 1 plus R 2 by R 1. So, in both the cases you do have, if your amplification factor is very high, you can afford to have almost 0 gain in the closed loop configuration, right, and it only depends upon the resistors, the ratio of the resistors. So, you change the value of R 2 and R 1 and you can get variable resistance, a variable gain with respect to your requirements, right, and that is what an important part is. So, let me recapitulate what we learned from this small module which we discussed now, is that to minimize the dependence of closed loop gain on the value of open loop gain, we should make 1 plus R 2 by R 1 much smaller than A, actually this should be smaller than A here, much smaller than A, right, and the inverting configuration suffers from low input impedance. So, inverting configuration has a problem, we did not discuss this, but we will come to this in the next module, that they suffer from a low input resistances. So, input resistance is pretty small in case of inverting configurations, right. When we meet next time, we will take care of voltage follower networks, and then we will look into op amp as an integrator, as a differentiator, so, and we will look into as a weighted summer. So, all these 4 or 5 configurations we will finish in the next turn, so that we are able to have op amp as a circuit element for the purpose of amplification, right, and that is an important phase. So, this module takes care, most of this and the subsequent module will take care of the analog design, and then we will revisit the combinational logical design at the last part of our module, right. Thanks a lot for your patient hearing, and thanks a lot.